In the last lecture, I mentioned the foundation of dynamics. It was laid by Sir Isaac Newton in his famous book, Principles of Mathematics, published in Latin in 1687. Sir Isaac Newton, and the front page of this very famous book written in Latin about twice as long ago as the first Christmas lecture was given in the Royal Institution. For the first time, the mystery of how things moved was solved. Newton's discovery has been the basis of engineering dynamics ever since. The result now appears simple, but it took nearly 2,000 years after the ancient Greeks discovered why things stay still, that's moving, before we began to understand what it is that makes things move. It was a stupendous discovery. The slide shows the central idea. This was Newton's famous second law, and it looks very simple, and it merely establishes, I say merely, but that's because it looks simple. What it says is that the force acting on a body of mass m will cause an acceleration of the mass in the direction of the force, and that acceleration will be proportional to the force. And the mass enters into the equation in the way that you see. But in doing this, Newton had to discover and think about the definition of mass and of acceleration, so it wasn't quite as simple as it may now appear, but very important. And before Newton, one of the difficulties in the way of the discovery was the way in which things moved in air. Many people had tried to measure the movement of things, but they hadn't appreciated that air itself will exert a force on moving objects, and that rather confused the entire picture. But if we do a little experiment in which there is no air, then the position is made fairly plain. And inside this evacuated tube, we have a cluster of feathers lying on the bottom just now, together with a coin. Very different masses, but no air in the tube. If I turn the tube over suddenly, since the force acting on each of the parts is the weight, which is proportional to the mass, then if the weight is proportional to the mass, the acceleration should be the same. So if I turn this up fairly rapidly, then with any luck, the feathers will come down at the same speed and the same acceleration as the coin. And you can see that's not a bad result. Now, if I open the valve and let the air in, here hissing through, and repeat the experiment, now I have air getting into the act, and of course the position is very different. And that action puzzled many experimenters for years before the truth became apparent. Moreover, again from the ideas of force and acceleration, if for the same body we double the force, then the acceleration should be doubled too. The mass is the same. So let's do an experiment and shoot an arrow in the air. And for that, I will shortly ask for a volunteer. But first, let me explain what I'll ask him to do. Here's the bow, and there's the arrow. And I'll need somebody who can hold it and shoot the arrow in the air. And we have some marks on the arrow to indicate the strength of the pull. On mark number 1, just there, a certain force is produced on the arrow by the string. At mark number 2, about double the extension. It's about double the force. Now the question is, if I double the force, how much faster does the arrow go? Well, if I double the force to begin with, then the initial acceleration should be double. So it accelerates with the string still pushing the arrow twice as fast in that position. Moreover, the distance through which the string pushes the arrow is twice as great too. In other words, the big pull is the same as the little pull, except that the unit of length is doubled. And that should mean that the velocity of the arrow leaving the bow is twice. So let's assume that that's the case for the minute and do the experiment. Of course, if the velocity is twice when it leaves, then since it will take twice as long to get to the top, and since the average speed will be twice as much, it should go 4 times as high. Twice the time, twice the speed, 4 times the distance. So that's the proposal. Now, if you could have a volunteer, perhaps someone, perhaps in the red jersey there. Your name is? Martin. Malcolm, okay. Would you like to face that way and shoot it up so it doesn't actually hit anybody, starting off in that position to begin with your, can I just show you, take your hand off it, put your thumb about there, and then the next time when it comes down, about there, okay? You have to guess the distances involved, but see if it comes out about right. That's number 1. That's about right. And I'll give it a good pull just past the other mark. And that, I think, perhaps, could you do it just a little more than that? You were holding it with your fingers slightly as it came away, and give it a slightly larger pull. Don't be afraid it'll go too far. That's probably more like it. Okay, straight up. And if you're guessing, then remember he starts from about here, and although it may not be exactly, thank you very much, Malcolm. Probably not exactly 4 times as far, but certainly more than twice from Malcolm's height when he started. So you can see that there's possibly some truth in the idea after all. Now, a familiar example of force and acceleration is something going around a circle at the end of a piece of string. And if I come around to the front and make this rather soft ball at the end of a piece of string go around the circle, then as it's doing that, if we neglect gravity for a moment and just think of the forces in the string, the gravitational effect is quite small. Then if I release the ball, or release the string anyway, then of course it should not fly out. The force in the string stops, everything is changed. And with no force, no acceleration, the ball should then go in a straight line, in the direction where I leave it. Now I'm going to try and release it with my hand in that direction. And then, of course, it should fly that way. So if you, in about the 4th or 5th row, will be prepared to duck, if I get the shot right, then we'll see how it goes. You see, it did actually go in that direction, so that the absence of a force means that things go in a straight line. If the effect of gravity is important, the result is rather different. And here we have a model of a little aeroplane which can be driven by a propeller at the tail. And if I release it with the propeller going, so now switch on, if I can start it in the right direction, it'll line up in a minute. It goes round in a circle, and there the resultant force on the aeroplane is made up of the tension in the string and its own weight. And the two of them combine to form the resultant precisely in towards the center of the circle. And you can see that as the speed goes up, then the angle of the string changes. And of course, the acceleration is that much faster. So the tension increases and the angle changes too. And that's quite a good stop. Now, although that's a toy, the principle is widely used and has been used for a very long time in speed governors for the control of engines, of machinery. The principle is exactly the same, and it's illustrated by this little model we have here. Let me tell you what it's made up of. It's made up of a couple of flyweights on the linkage, mounted on a shaft which can be driven about a vertical axis, and we suppose that there's an engine driving it. In fact, there's a small electric motor underneath, which I can switch on and will in a minute, and that will drive this around at a certain speed. Now, the idea is that if this is a large mechanical machine, for example, and if for some reason the load should change, we would like to keep the speed constant. That's maybe very important. And this is a device that will do just that. So if I turn the electric motor on, you can see it's driving around. The links come out. And in doing that, they move another link here which controls the fuel supply. In this case, it's the electric voltage. And that means that if the speed, for some reason, changing load perhaps, should change, suppose the speed goes down, then the flyweights will go down. This linkage will operate a valve and will increase the fuel supply, and so the speed will go up again. So the basis of that provides what's called speed governing and is widely used on large machinery. This sets the speed, so I can turn it up or turn it down according to that control. It's an application that's been used for many years, first in windmills and then by James Watt, perhaps the best known of all, to control the speed of his steam engines. Another experiment with circular motion is to make the plane of the circle vertical. And we'll do a few experiments on that. The first one is very simple, and we'll introduce the others. Now, this is a rather harder goal, but I'm not going to release it this time. But turn it in a vertical plane. And it's pretty obvious that when the thing is going through the bottom position, the weight increases the tension in the string. In the top position, it will decrease the tension of the string. So if I turn it fast enough, then the string will remain taut and the weight will not overcome the tension in the top position. But if the speed falls, then you can see it falls out of orbit and the motion is lost. Now, the same idea applies with small toy cars that you've seen going around on circuits like that, and perhaps a couple of volunteers somewhere, somebody, yeah, could you like to come down? And perhaps from the next row, someone, would you like to come down as well? It needs two people to do this. Your name is?
John.
John and?
Andrew.
Andrew. If John would like to go to that side, Andrew come to this side. Andrew will release the, is Andrew this side?
Yes.
Yes. If Andrew will release the car on this side, then if he gets it going fast enough, it will in fact go around the loop. And then John, who's very quick, will catch it to the other side as it flies off. Experiment number one. Number two, Andrew will release it from that height, which we've marked out beforehand, and then it'll fall out of orbit, just at the top point. So if you'd like to start by some fairly high position like that, and just keep this flat, keep that clear, and we'll see if he can catch it. That's very easy, yeah. Okay, that's good. Now, in the lower one, it doesn't quite make it, so I'm sorry, only one catch. Now, thank you very much. If you'd like to see that in slow motion, then I think we can play that back to you, and you can see the detail of the motion. That's the one that just fell out at the top of the orbit, and away she goes. It didn't quite make it round the circuit. Now, yet another example of things falling out of vertical circles is water in a bucket. And if you do want to try this experiment yourself, may I suggest you do it out of doors, and preferably wearing a nice big hat. But Mr. Jameson is an expert, and he will first of all demonstrate there's actually water in the bucket, and we'll do a circuit or two. And it's really very easy. Now, the trick is not to make it go as fast as you can, but if you are trying it yourself, make it go as slow as you can. Very good. So obviously he just gone past the point at which the water would stay happily at the top of the bucket and be held down by the pressure on the base. If the time in which the force acts is very short and the force is not too large, then the body will not have much time to accelerate and its velocity will be very low. In other words, it will stay almost still. So here we have a rather famous experiment. And again, we'll have a volunteer, I think, in due course. But let's see if it works first. Here the only force between the cups and the table in this direction will be the friction when I pull the tablecloth. Now, if I pull it fast enough, then it will not have much time to cause an acceleration of the cups, will it? And so the cups will then stay still. And because we are very confident, we're going to put some water in, do you think? Since we think this is going to be okay, we'll try a little water in the cups and try a quick snatch. So that's fine. Okay. We have a little water just on the tablecloth, but let's hope that that doesn't affect us too much. So standing back and cheating slightly, we give it 1, 2, and 3. So it does that. So, somebody up there like to come and try this? Anybody? Okay, come on. No, he's saying he can't guarantee it, but then neither could I, so that... the way to do it is to take... hold it like that, and give it a quick snatch, straight back, not up, but if anything down. Quick as you can. 1, 2, 3, go. Very good. Excellent. Thanks very much. That's good. If we want to know how large bodies turn as well as move forward, then the most important point of all is the center of mass of the body. So this is a pointer which is not quite symmetrical, as you can see, not uniforms, and we can find where the center of mass is by just balancing it. So that's the center of mass. Now, the thing is, I need another volunteer for this. So is there somebody, perhaps somebody at the back there? Would you like to come forward? Yeah, in the red jersey. That's it. That's it. Very good. Your name is? David. Okay. You have to catch this, okay? Stand over there a little bit, slightly to one side. It'll be quite easy. The point is that if we think of this being outside gravity, it's not a bad approximation. The weight acts straight down, the reaction is straight up, they're in balance more or less. The friction is very low. And I'm going to give this pointer a sharp tap above the center of mass, in which case it'll move to that side and turn over in that direction as it goes. And then perhaps you can give it back to me. That's the easy bit. Right, so obviously that's what it does. Now, could you stand a little bit to the side? Okay, that's right. You can perhaps see it coming better. Now, if I hit it below the center of mass, then it will again move to the left, but this time it should turn the opposite direction. You ready, David? Oh, you caught it. Very good. That's good. Now, say that we haven't finished yet. One more try. Now, if I hit it exactly at the center of mass, then it shouldn't turn at all. Ready? Very good try. Thank you very much. So the center of mass is really rather an important point, certainly so far as angular motion of bodies is concerned, and we can show that on the slide. If you look at... I've lost my pointer now. That's fine, thanks. If you look at this side of it, then you'll see that if we have a torque or the turning effect of a force applied to something that can turn about an axis, it will in fact create an acceleration, call it alpha. And the relation between the torque and the acceleration is just the same as in Newton's law, except we're talking now about circular motion. And instead of mass, we have a quantity called moment of inertia, which is related to mass and the distribution of mass about the axis in question. And that's a rather important feature of angular acceleration, which we'll return to shortly. Now, for our next experiments, we use Newton's law in a slightly different form, shown on the next picture, which applies to bodies whose mass may change. The way it was expressed beforehand is perfectly good, provided the mass remains constant. But if the mass varies, then we have to look to a different arrangement. And the expression now is, instead of mass times acceleration or rate of change of velocity, it's the rate of change of mass times velocity, the product. And that product is called linear momentum. Now, it follows that if the force is zero, no force, that the linear momentum then doesn't change. It remains constant. And that's a very important characteristic, which is used in rockets and for propulsion, in which the jet is emitted from the moving object. In fact, the film that we have coming up demonstrates the takeoff of Apollo 14 many years ago on its successful way to the moon. There, the engineering, of course, is very complicated for the combustion, the control, and the mechanics, so that great efforts have to be applied. But our experiments will be somewhat simpler. We have some rockets, two sorts of rockets, in fact, to show you. The first set are available in the way of compressed air rockets, and if we'd like you to do one or two trials with these. So Bill and Melanie and Alan, if you could distribute these. Don't let them go for the moment, though, because we'll just watch one going. That's a bit curved. I'm not sure how that's going to go, but let that one go first. We'll see what happens. Okay. Oh, that's very clever. That's very good. Now, perhaps if you would like to leave those two go simultaneously, then we'll see what happens to them. Okay, take off. So. It's a very complicated motion. Thank you very much. We also have some water-propelled rockets. Air is not a bad propulsive medium, but it's rather light, and if we can spray water out of the exhaust, then so much the better. So we have a couple of rockets here. One will be given more pressure being applied with an air pump, so there's air inside as well as water. And the one on that side will have rather less pressure than the air on that side, so the water will come out of that more slowly. And as a result, we do not think it will go quite as far. So, and then we'll release that and we'll compare. So we'll have a lift-off on that. 5, 4, 3, 2, 1, lift-off. Oh, well, that's not bad. And of course, it comes down again. Now, this one should make the whole distance. 5, 4, 3, 2, 1, lift-off. And that was great. Now, if I can just dry my notes out here briefly for the moment. Similar ideas, of course, apply to rotating systems. And here, Mr. Coates has a very early form of turbine, nothing like Parsons' turbine that we saw last time, but nevertheless, a simple turbine device. And inside the sphere, water is being boiled, steam is ejected from jets which are pointed tangentially, and the exhausting steam produced, rather like the rockets, the thrust in the other direction, and drive that round, as you can see, at quite a merry rate. In fact, a very similar idea is used for the attitude control of satellites. There you see a large satellite floating about in space, and it's very important that the satellite should be set up in the right direction. The attitude of the satellite is extremely important. One way in which that is achieved is by means of minute gas jets, which I hope you can see here, tiny jets of gas, which under the control of a computer on board the satellite, will emit small, tiny pulses of gas and slowly turn the satellite in the required direction. These jets are situated strategically around the structure of the satellite and so permit control. It's not the only control on the satellite, but it's a very important part of the whole control system. Now, we can illustrate these matters even more visibly by means of a special chair. This chair is rather unusual in that, oh, we have some water underneath it. That's interesting. But let's see if it will lift off. I think it's going, Bill. Now, the compressed air is fed through that pipe to the feet of the chair. There are 3 feet. And there are small jets drilled into the bottom of the feet, which just lift the chair off. It's a kind of hover chair. And with any luck, I'll get that underneath. And now it's floating on top of the paper. So it's not actually in contact with the glass. And that means that the friction is extremely low. And if I mount this chair in a suitable position on this side, then I should be able to propel myself in a backward direction. She's going, I think. I'll just hold myself there with a suitable drive. Okay? Clear? So we'll try it and see if it works. And you perhaps could duck a little bit if you get too much. Am I clear to the middle? You can see. On the other hand, if I wish to, the camera, if I wish to turn, but I can turn in that direction, or with any luck, if there's any gas left in the thing, turn in the other direction. So you can see that both linear and angular motion. Now, we'd like a volunteer to come and do something very similar, but not quite the same. We need a good strong. Okay, that young man there. Okay. Yes. Would you like to come? Your name is?
James.
James, okay. Right, if you'd like to sit on there, James. Now, this has to do with angular motion, and there's a very similar proposition about angular momentum. That is to say, if there's no torque, then the angular momentum will remain the same. And here, James is sitting down. There's no talk about the vertical axis. But we'll drive up a wheel. Okay, that's not too fast. Now that has a lot of angular momentum. So if I give it to James, it's quite safe. Hang on to it firmly there, and then turn it either way up you like. That way. Turn it right round. Okay, now back again. He turns in one direction, up again, and he goes the other way. Down, right round, and back again. And you can see, thank you very much, James, that's fine. So the angular momentum of James plus the wheel was conserved, as you can see. If the wheel turned in one direction, he had to go the other way, so that the net result of the angular momentum would be 0. We shall be looking at jet engines later in the lectures, but for the time being, simply regard the jet engine as a means of producing thrust. That's a very famous engine. It's the Pegasus, and it goes in the Harrier jump jet. And it has 4 nozzles arranged on the side of the aircraft under the pilot's control as to direction. the result is called vectored thrust, and it gives the Harrier, as you must have seen, extremely good maneuverability. Under the pilot's control, the nozzles can be either directed backwards, so that the aircraft is given forward propulsion. The front of the aeroplane is that way. Or else, if he wants lift, then turning these nozzles in the downward direction produces the jet exhaust going downwards, and that produces lift. So that can keep the aeroplane up, even though there are no aerodynamic forces at all under the wings to provide the normal, conventional lift. And then by virtue of combinations in between, he can get partial lift and partial propulsion according to the particular position of the nozzles. A very successful and extremely maneuverable arrangement. So if we have a look at the next slide, you can see that the configuration is rather important. The engine is situated amidships, and in order to ensure that the aeroplane doesn't turn when the nozzles are pointing downwards, the resultant engine thrust line must go through the center of mass, rather similar to the stick that we were demonstrating a few minutes ago. So that has to be in exactly the same line as the weight of the aircraft, otherwise the aircraft would not be able to maintain a level position. The next slide shows that in addition to the main engine nozzles, there are some small thrusters positioned at the nose, the tail, and the wingtips under the control of the pilot, so that he can, by adjustment of the jets issuing from those nozzles, obtain extreme maneuverability, as you will see in the film. This particular Harrier has been flown by the chief test pilot, John Farley, and the film was taken in Switzerland on the demonstration flight. And there you can see the astonishing way in which this aircraft can be flown. There are not many aircraft, I think you'll agree, that can go backwards like that, but that's doing it quite successfully. He'll turn around and bow in a minute, I think, to the waiting stand. Just perhaps acknowledging them now, and then beating a graceful retreat. So that's how the Harrier provides its maneuverability. Ideas of impact are closely connected with momentum that we've been talking about. The thing about impact, of course, is that the period of the action is very short, and very complicated things can happen during that very short interval. Not all of them are fully understood. A good example is this little toy, Newton's cradle, it's sometimes called. It consists of 7 large ball bearings which can swing just like a pendulum. And if I release one of these, it will strike the other 6, and one comes off the other side. I expect you've seen this happen before, perhaps played with these things yourself. You get 2 off and so on. And the point is that if you take the system as a whole, that when this ball strikes the other 6, it has a certain linear momentum. And therefore, since there is no horizontal force acting on the system as a whole, the velocity of this one coming off the other side must be the same if the linear momentum is to stay constant, which it must since there's no force. But then you may say, well, why just the one ball coming off that side? Why not 2 coming off at half speed? Because that would be the same linear momentum. Well, the answer is that not only is linear momentum conserved, but energy is conserved too. And since energy depends on the square of the velocity, the only way in which both energy and momentum can be conserved is that 1 down, 1 up, 2 down, 2 up, and so on. If you put 3 down, now striking 4, then you get 3 up, 1 stays in the middle. If I bring 4 up, 2, 3, 4, there are only 3 left. So you might like to think what could happen now, since we still insist that momentum and energy must be conserved.
Once you're swinging, keep swinging.
Yeah, that's right. That's very accurate. And as you see, one switches from side to side so that nature is not foiled. And it's a very interesting little example of mechanics. Now, the advantage of soft connections and impact can be illustrated with the famous broom shank and saw experiment. And it's an arrangement in which we put that piece of wood with small pins at the end, these are the soft connections, on two very fragile wine glasses, and deliver a mighty blow with a sword, which is a replica of the 4th Legion 2,000 years ago in Newcastle upon Tyne. Mr. Coates, however, is much more modern than that, and he will deliver a mighty blow, and you'll see what happens. No harm. Well done, Dole. That's very good. The pin supporting the broom shank, or the piece of wood, collapse first, of course, and before any shock can be transmitted to the wine glasses, the action has passed and the wine glasses are safe. Another kind of protection can be provided by wrapping a fragile object in suitable wrapping. And if we have our egg box, I think we'll perhaps just try that next. This is a very temperamental experiment, I'd better say. Inside the box is an egg, and we'll prove it to you afterwards. And there's a certain amount of wrapping inside to protect the egg. So there was a volunteer who was offering over in that quarter before. Would you like to come up and try this? The egg is quite uncooked. So if you just take it and drop it from that height, which is quite a modest height, not very much impact there, I think, but we'll just confirm that the egg is still in good working order as an egg. Your name is?
Mariska.
Mariska.
Yes.
So there, in fact, is the egg, intact. We put it back in its little nest and wrap it up again. That seems to be going the other way, doesn't it? So that we have a slight problem. That one has come off. We'll have to take that out. We take that right off there, pin it around that way. And this time we throw Mariska will throw the box up to a height of several feet. Just give it a little throw up like that, and we'll have a look when it comes down again. Right up, that's it. That was quite a difficult landing, as you probably noticed, on the corner. So let's hastily tear the box apart and see. And it's still there, and it's still intact. Thank you very much. That was a very expert throw. Now you may well say that the egg is hard-boiled. But it isn't. It's a genuine uncooked egg. So such problems are really of very great importance, especially for people who, like the egg, are rather fragile objects, often traveling at high speed inside steel boxes on wheels. The next film will show the extent of damage that can be caused by quite modest collisions. This first sequence was taken at the Motor Industry Research Establishment of a car sent at 30 miles an hour into a fixed object, concrete block. Here's another rather elegant car going forward with a better crumple resistance at the front end. And this is the sideways roll. The car is well instrumented, and you can see that the wires coming out are connected to the car and will be recording deformations of the structure and accelerations at various points. Perhaps surprising that the car will keep on rolling to that extent, but as you can see, it goes on after the film is finished. These films demonstrate seat belts. They were taken at the Transport and Road Research Laboratory, and there both front and rear passengers have seat belts. 30 miles an hour again at impact. Now there, neither has impact, and you can see that that result would be disastrous. Now, the front man has a seat belt, but not the rear. And finally, loose objects in the back of the car. So those are quite modest speeds, 30 miles an hour. We've got an experiment here which we'll ask some volunteers to help us with in a minute. These two cars are made of cardboard, and they have drivers in. One has a seat belt, that's that one, and the other one doesn't. No, wait a bit, that one does not have a seat belt, right? And that one does have a seat belt. So that's the way round. The man without a seat belt is quite precariously poised, actually, because it's difficult to keep him up there unless he's got a seat belt in, of course, to start the experiment. But by various means, he's suspended temporarily. We think that the little bits of cotton thread holding him will break when he comes down on impact. We can release both of these, and we'll do that, and then perhaps play one of them back in slow motion. So we need someone to come down and pull the trigger. Some great strong fellow, perhaps on the end there. Would you like to come down? Now, we go out and we'll take the man without the seat belt first, and that's the chap on that side. Yes? So come around this side. All you have to do is to pull that fairly sharply towards you, and that will release this, you see, and down she'll come. So if you're ready for that, take a good hold of it and be ready to pull quite hard. Right. Oh, up to much. Very good. Thank you very much. Okay. Now we have a replay in slow motion of the driver who came down with no seat belt. It'll be coming up in a minute, and you'll see that, in fact, without any protection, he's in a very dangerous state. Now, it's just coming back, and you can see it's coming down, hitting, and he goes flying out of the car. Whereas the other man, held into the seat belt, is very much better off. Okay? Thank you, Adrian. That was very well done. Let us return briefly to the subject of angular momentum. One of its most remarkable manifestations is the gyroscope. Now, the gyroscope is simply a spinning wheel or a spinning body whose axis is free to turn in any direction in space, either by way of a mechanical suspension or, as in a very familiar example, the case of the Earth. So if we have the next slide, to look at, this represents the Earth, which is spinning at one revolution per day, very slowly, about its north-south axis. But although the spin is very slow, the Earth, of course, has an enormous moment of inertia, and so its angular momentum is correspondingly large. And that angular momentum, like other gyroscopes, produces stability in the direction of the axis. So that by the time the Earth has come around 6 months later to the other side of the Sun, then the axis is still pointing in space in the same direction. And that stability of the axis is conferred by the rather slow spin, but the very large angular momentum about that axis. And this is a very important characteristic of spinning bodies, as we shall see in a moment. In fact, applying spin to things is a very well-known method of ensuring stabilities. Bullets fired from rifle barrels spin, and so they keep pointing in the same direction. And those who are familiar with rugby and can throw the ball well, I can't, but I think Melanie probably can, well, not bad, can spin the ball as they throw it, and so preserve the direction of the ball, and so it's more liable to go in a straight trajectory or where you want it to. Now, if I throw this roughly in that direction, perhaps you could just get ready to somebody to catch it, and I'll try and spin it, not very expertly, about that axis as it goes. So if you're ready there, we'll see whether it will keep stable in that direction as it goes. And it wasn't bad. If I were a better thrower, it would be even more stable. Perhaps you could pass it down slow or even throw it down. That's very good. Thank you. But there's one thing that you need to know, and that is that you have to be careful about the axis of spin if the body is not symmetrical. And this applies to satellites. Satellites which are stabilized by spin are stabilized about the certain axis of the largest moment of inertia. And here we have an example of something that is made up by ourselves, just a block of wood with two pieces of steel thread, perfectly balanced on the point of suspension. If I release it, other way, then the cord will unwind, but it's really quite unstable, and it flops over to one side. And although the spin is picking up, there's no improvement. Now, if we take out the two metal rods, the state of balance is still the same. The center of mass is still where it was. But now if I start the spin going, then it's perfectly stable. And the difference between the two lies in the mysteries of moments of inertia. And in the first instance, it turned out that that axis was not a stable axis as regards the spin. The moment of inertia was the intermediate one. There are three principal values. That was the one in the middle, and as a result, instability. So satellites are stabilized about one of the other axes, usually the one of maximum moment of inertia. Now, if we come to the gyroscope proper, here is an example of a mechanical gyroscope consisting of a rotor in two frames. The rotor can be spun. We'll spin it in a minute. One frame can turn that way. One frame can turn that way, so the axis could actually point anywhere in space. So now if we drive that up in speed, we can see that we'll get extreme stability and also a peculiar motion called precession. Mr. Jameson will drive it up. Now, it's spinning away quite happily, and it really is quite stable. As you can see, if I give the outer gimbal quite a sizable tap with a hammer, then it moves very little. This is waggling at the end, but that's just the flexibility. So it's really quite stable. Moreover, if I push in this direction down here, you see the axis moves in quite the other way at right angles. And that's the so-called precessional movement. It's really fairly simple to understand, provided the motion is steady. What happens is this angular momentum vector, it's the vector associated with the spin about that axis, moves in the direction of the torque vector. The torque vector, if I push down there, points in that direction, i.e. about that axis. And so it will move the angular momentum in the direction of the torque. That is, the torque is the rate of change of the angular momentum vector. So it's quite easy to remember those directions if you think of these arrows, one for torque, one for angular momentum, and away she goes. Now the slide shows a device that was invented about the turn of the century by an inventor in this country for a two-wheel car. And those four Edwardian gentlemen are actually sitting on top of a large wheel inside the body of the car in that sort of configuration, keeping the car stable on two wheels. It was never successful, although in fact it was technically quite adequate, and the car was driven from London to Birmingham and back several times, I believe, but it never caught on with the public's approval, and instead two-wheel vehicles of a rather different kind, motorbikes and bicycles. But it was an interesting technical idea. Now, the next gyroscope we'll show you, I think, will be the top, or perhaps the tightrope. Let's do the tightrope if we can get that started up. Demonstrating a stability of a similar kind. Would you like to hold that? Good. This is a two-wheeled vehicle, if you like, and we'll start it off with the wheels balanced rather precariously, up a little bit, Bill, and it will, with any luck, stay there, but run down the tightrope. And there she goes. It wasn't quite on the wheel, so we'll put that back in that position, and now it should be all right. And it goes right down to the other side, and we can run it backwards by dropping the far end. And again, it runs down in quite a stable way. Similar to the Shklovsky car, in fact. And finally, the very familiar kind of toy, or at least it was once familiar, the top. And here we can produce the action of two tops, one on top of the other. And this illustrates precession. And you see, we could keep on building up like that, and it really remains very stable, and it's a very nice thing to watch. Fine. Thank you, Alan. Good. Now, as I mentioned, the gyroscope is not simply a toy, and we have one or two examples of the ways in which it can be used to stabilize objects in practice. This, for example, is a real momentum wheel, as it's called, used in British aerospace satellites. It would take us too far afield to explain precisely how it works, but it acts somewhat like a gyroscope. It's carried in the body of the satellite, and by virtue of its stability in spin, that it confers a degree of stability upon the satellite. It's very carefully controlled, and as you can see, it's rather a beautifully made wheel. Another example is this instrument which we stuck up on the stands, and we hope we can show you the effect of stabilization for this. It is, in fact, it's not quite a binoculars, it's a monocular. It has one eyepiece, and it should be used by someone looking through it from this side up towards the lights, let's say. But because the camera can't look down the lens, we've done it the other way around. And so you can see, I hope, an image of one of the lights on the white card. Now, within this is a very clever device. It's a little gyroscope with a linkage inside that actually stabilizes the mirror and the image as it comes through the eyepiece. So if we can have a volunteer somewhere nearby who hasn't come up before, would you like to come up? And we can demonstrate how this stability works. Now, if you come around this side and just tap the instrument lightly with your finger, then you can see that the camera's picking up if the camera's picking up, you can see the image is vibrating. And now I'm going to uncage the gyroscope that puts the gyroscope into effective action and ask you, your name is?
Yvonne.
Yvonne, to do the same thing while the gyroscope is operational. Right, could you tap it now? And you can see it's really very stable. Now I'll encage the gyroscope again. Right, tap it once more. And you can see it moves around quite significantly. And once more, Yvonne, tap. It's not that I'm holding it, but inside thank you very much, inside the casing, this gyroscope is actually doing all the work and holding the thing in a stable position. It means that somebody looking, good, thank you. It means that somebody looking through it and trying to read something at the distance has his range of identification increased probably by a factor of 3 or 4. The magnification is 7, but the important thing is that if somebody's trying to read in a moving vehicle of some kind, then it's bound to shake, and if your hands are shaky anyway, you've got a problem. But this gyroscope would take care of it and would stop the small vibrations of the image. But perhaps the most important application of gyroscopes is for inertial navigation. And to explain that, if I just have the next picture, we can have a look and see what looks like a very complicated system. Let me say what it's used for. It's used for the navigation of aircraft. Practically all large civil aircraft now carry inertial navigation equipment. And they automatically record the motion of the aeroplane through space with great accuracy. The accuracy is a fraction of a mile in 1,000 miles. And the way the system works is shown on this slide. We have a number of gimbal rings, rather like the ones we saw on the model there. And this is the outer gimbal ring, which is connected to the aircraft. Inside that, there's another ring. This ring can move about that axis. Inside that, there's another assembly which can move about that axis. And at the heart of the system, there's a stabilized platform, stabilized by 3 gyroscopes. The way it works is that the gyroscopes hold the platform very steady in space. No matter how the aircraft may move, they'll maintain stability to a very high degree. The platform carries 3 little instruments called accelerometers, and they measure the acceleration in 3 directions very accurately again. So if you measure the accelerations, then you can find out, compute the velocities, compute the displacement. Provided the thing is set up correctly to begin with, it can register the actual position of the aircraft without any external references at all. These are the actual hardware, the pieces involved. This is the little gyroscope, and it's very tiny. It's a marvel of precision manufacture. Inside, the rotor turns at a very high speed. Of course, it's cut away now so that you can see it. And that rotor is inside a casing that can move just a little bit about this axis. So that if it's turned about that axis, then it will, in fact, just like the model we saw, rotate slightly about the other axis. That's picked up by the control system, and that puts into the stabilization. Now, the next stage up, that's 1 gyroscope. The next assembly consists of 3 gyroscopes inside the casing, 1, 2, and 3. And they're sensitive to rotations about that axis, or about that axis, about all 3 axes. And they'll measure that with great accuracy. And finally, that is nested inside this box of tricks, which has these various frames that I mentioned a minute ago. And the one that you can see now is, in fact, this piece fitting inside the other frames. And that then is installed in the aircraft. So that's an inertial navigator. And most civil aircraft now carry 3 for cross-checking one against the other. The result is an extraordinary feat of precision engineering that's incorporated in these aircraft and also made space exploration possible. But the last thing that I want to show you is what might be called a physicist's gyroscope, i.e. it has no moving parts and it depends upon the action of the laser beam. These are under development now, and there is no doubt that they'll have importance in the future. We've just turned on the laser beam. You can't actually see the lasers, but you can see the discharge tube at the top. And if I just move it around there and then back again so everybody can see what's happening. The laser beam, in fact, is sent around 3 sides of a triangle, an equilateral triangle. There are 2 laser beams. Incidentally, the laser is a helium neon laser. One beam travels in one direction and the other beam travels in the other direction. They are combined after they've gone round the 3 sides of the triangle. So what happens is that if this is turned when the lasers are traveling around the circuit at, of course, very high speed with a very high frequency, the laser going around in that direction has to travel rather further before it comes back to the starting point than the one going the opposite way because of the motion of the case. And that tiny difference is reflected and a slight change in frequency of the opposite lasers. When the lasers are recombined, they then produce fringe patterns which are a measure of the rate of turn. And certainly the possibility has many attractions, not least no moving parts. But it also has its problems, and so there may be some time yet before they're as widely accepted as the more familiar mechanical gyroscopes. Well, that covers most of our activities today, but we'll leave you So perhaps we can finish the lecture in the same way as we began, by showing you this rather graceful motion of a gyroscope suspended in a very long piece of string and spinning away merrily. And if I send it out in a circuit, then it will come back and move around in a nice circular motion. Tomorrow I shall be talking about mechanical vibration, and there'll be a set of experiments that I hope you'll like to see. Thank you.